Now, O2 is the molecule that will be created here. So, because there is a 2 next to the oxygen, that means that there are 2 oxygens, and each oxygen has 6 valence electrons. So 6 times 2 is 12 valence electrons. Now, there is oxygen and oxygen. So because there are 2 oxygens, there will not be a central atom that we will be looking at, and I will explain how to go about using the VSEPR reference table as a result. So each oxygen has 6 valence electrons. I'll just label it based on the way I've shown in the past on creating Lewis structures by making sure to put 1 electron on each side until each side has a maximum of 2 valence electrons, and the total number of valence electrons to start off with are present. So since oxygen has 6 valence electrons, here in each oxygen there are 6 valence electrons. All right, now I am going to have to fill the valence shells of each oxygen. And in order to fill the valence shells, there needs to be bonds formed that are that show electrons being shared, because that's what would happen in a covalent bond in order for each oxygen to have 8 valence electrons. So there will be a bond formed between an unpaired electron on each oxygen. Once this happens, we see that each oxygen, since it's the same on both sides, each oxygen has 2, 4, 5, 6, 7 valence electrons. And we can verify and count on the right side as well. 1, 2, 3, 4, 5, 6, 7. So each oxygen has 7 valence electrons. Now, in order to fill the valence shell, there needs to be one more electron added to each oxygen. As a result, another bond will be formed. Another bond is formed because the valence shell for each oxygen needs to be filled. And it's filled when there are 8 valence electrons. So now let's count again. 2, 4, 6, 8. And then on the other side, 2, 4, 6, 8. So the valence shell is filled. Let's create our final structure. Now, so now we're going to determine the VSEPR shape for O2. In order to do this, we're going to count the number of sides with bonds. So I'm just going to pick one oxygen. It doesn't matter which one because it's the same on both sides. So I'm going to pick one oxygen and count the number of sides with bonds. Not the number of bonds, but the number of sides with bonds. So here in O2, there are 1, 2, 3 potential locations for bonds. However, there's only one side of oxygen that has a bond, and there are 1, 2 sides with unbonded pairs, lone pairs, electrons that are not forming bonds. As a result, in the VSEPR reference table, I am going to look for 1, so sides with bonding electrons, there's 1. And I've highlighted all the ones in the first column. And then in the second column, there needs to be 2 because there's 2 sides with unbonded pairs. As a result, I will highlight the second 2 down. Why? Because I need to find the shape that corresponds to a molecule with the central atom that has 1 side with bonding electrons and 2 sides with unbonded pairs. As a result, the VSEPR shape, or the geometric shape for O2, is linear. Now, I can write linear next to O2. And also, to verify that my structure is correct, what I will do is I will count the number of valence electrons from each oxygen. So we know that the octet rule was filled. However, we did some calculations at the beginning in order to determine the number of electrons, valence electrons, that should be present in the molecule in total. So there's should be 12 valence electrons. Here there are 2, 4, 6, 8, 10, and 12 valence electrons. So now we know that we have the correct structure and we have the geometric shape. So here we go. There we go. We have the VSEPR notes: valence, shell, electron pair, repulsion. And each shape was represented in these notes. If you have questions about bent, trigonal pyramidal, trigonal planar, tetrahedral, how I got to any of those structures, please refer to my other videos. Thank you.